formula, so you know where it comes from, sort of, or at least you can trust the mathematicians that we did our job and got this nice formula for us. So now today we're going to be working with a few examples to see how this works. We'll return to Gabriel's trumpet, and I'm sure that you're excited about that because that one is, there's an interesting paradox that occurs when we look at the surface area of that object. But anyway, let's take a look at, well, we'll get back to that. Let's take a look at this example, then we'll come back to the idea of what happens when you go around the y-axis instead of the x-axis. Thankfully for us, not much changes when you change the axis of rotation. You just have to bear in mind the general formula and you'll be okay. So let's take a look at this. You can imagine taking a circle, or maybe what you could think of this as being a sphere that you've cut off the two edges, if you will. So it's like a bead, you know, beads that are spherical that have the two edges chunked off. And we want to know the surface area of the outside of this bead or this sphere where we've cut this off. And we're cutting it off just 1 to -1, but you could cut it off anywhere and you're going to have a similar situation with the surface area. So let me just change over to Notability for this one because that's going to be way easier. It's going to run out of room if I try to do it right here. So give me a sec. And by the way, what you're going to be doing first is finding the derivative because that's what we always do first when we're doing calculus, right? When in doubt, do a derivative. Okay, so here it is, paste it in there. Okay, so the reason why we're doing the derivative is because it's part of the formula. Let me just write down the formula for you to remind you what it is. So this is going to be the integral of 2 pi r times the square root of 1 plus the derivative squared. I'll put dx there. So the r is the thing that we have to pay attention to. That's the only thing that will change when we change our focus from rotating around one axis to rotating around another axis. Everything else is the same, which is kind of nice for this. It was different when you dealt with shells and washers. That was always so confusing. So we need our derivative. There's the function y is equal to 4 minus x squared. Let's get our derivative. Go ahead and jot it down. I'll find my randomizer so that you guys can all enjoy being chosen. Let's see. Oh, I have to fix my attendance as well. Give me a sec. Manage. Here we are. All right, all done. All right, who is the first volunteer? Oh, not here. But Simon is here. Simon, you know the derivative of that. You can use the chain rule, right? Just a minute, just so that because I know you know how to do it, but just in case there are others who are not sure, you probably are doing this sort of thing, 4 minus x squared to the 1/2 power, and then using the chain rule. So go ahead, Simon. Tell me what your derivative is. That stuff. Okay, go ahead. Beautiful. So you know the chain rule that you're going to be multiplying by that derivative, right? Beautiful. So there it is. So there's our derivative. Let me clean that up a little bit because it'll probably look a little bit better if I just move some things around. So this will be negative x over the square root of 4 minus x squared. You might wonder where everything ended up. First off, the 2's canceled with one another. The negative 1/2 power shoved that into the denominator. And then, of course, the x and the negative stayed around for the end here. Okay, so we've got that. Now let's put this into the formula for the surface area. So surface area, we're going to do the integral of 2 pi times the radius. Now, radius in this case, and it's always good to double check with your diagram. I didn't sketch the region, but this is kind of the region here, even though you have this kind of three-dimensional version of this. But so if you want to imagine just this portion, let's see, here is this rectangle, or so the radius is the distance to the function in this case. So in this case, now like I said, it's going to change when we change the axis, but for this particular case, the radius is the function. Okay, so 2 pi times the radius, and now things get really ugly because we're going to do the square root of 1 plus that derivative squared. And I suppose I should put some limits in here. So there it is. Let me just zoom out a bit so you can see it all, and it's all of its glory here. So yeah, I don't want to annotate it more than it already is, because that's already super confusing, isn't it? And that's so complicated. But let's not fear, because some magic is going to happen, I think. We're going to find out. Okay, so next step, let's persevere. Don't be afraid. Go ahead and do what we can. So let's combine all this stuff. By the way, you're going to find in your homework there are 2 versions or 2 types of problems you're going to be doing. One of those problems is going to say, hey, just punch it into your calculator. We're going to do that today with some of the problems we do. Some of them are going to say, work it out. When it says work it out, it means that if you do a little bit of algebra, some magic will happen, and you're going to be able to actually find the antiderivative. I got to be honest, I can't remember which version this is, but let's do what we can, see what kind of algebra. I think this one does work out, but just if it doesn't, I've got my calculators here, and I'm going to show you how to use them. Okay, so first things first, we're going to do a little bit of algebra. Here's what I'll do is I'll combine the 2 radicals. Sorry, we don't need a double radical there. So that we have 4 minus x squared times 1 plus x squared over 4 minus x squared. So I'll pause each, because the algebra, honestly, I mean, throughout the 28 years I've been teaching this here, it's not the calculus that causes the problems. It's always the algebra, usually the algebra, but also trig sometimes. And so you know how it is. So the algebra, tell me if you need me to explain some of this, I'm happy to do so. It is hard. We got it? Figured out where all the stuff went? I just combined them in 2 radicals. That's right. And then squared that, yeah. That's it. Yeah. So far, so good. Now we're going to do a little bit more algebra. I'll go slow again. So yell out if you need a little bit more of an explainer. So next step is to write this as a single fraction. You've got 1 plus this. I'm going to put it as a single fraction. So this will be 4 minus x squared, square root, times, and I've got 4 minus x squared plus x squared over 4 minus x squared. So just to explain, 1 is 4 minus x squared over 4 minus x squared. So if you combine this as a single fraction, you just add the numerators, 4 minus x squared plus x squared. And you probably, some of you are seeing the miracle that's about to occur. But let's go ahead and do it together so that we can enjoy it. So this is going to equal 2 pi times the integral from -1 to 1 of the square root of 4 minus x squared. What am I doing? That was not the right place for that parenthesis. Times 4 over 4 minus x squared, because the x squareds cancel with one another. Oh, how beautiful is this? So this is just that. And you could do this probably in your head at this point, but we might as well go ahead and do it together and enjoy the final answer. Oh, someone not here, but Christian's here. What's the antiderivative of 2? 2x, yes, so easy. So beautiful. So this will end up being, let's just combine it all. 4 pi x evaluated from -1 to +1. Wait. Something is not right. That should not, you should not end up with 0. Oh, no, you don't end up with 0. Duh, what am I thinking? Okay, no, I'm good. 4 pi minus negative 4 pi. Phew. Okay. I got scared for a minute that I'd made a mistake, but no, that looks good. Beautiful. Isn't that amazing? So cool when it works out so nicely. So it won't always though, but so you have, like I said, two different sections in the book. The first section says use your calculator. I'll show you how to do that, don't worry. The second section says just do it. And when it says that, it means that if you do enough algebra, you're going to find, oh, it's actually kind of easy. So up there, I mean, what a nightmare. Look at that. Who would have known that that was so easy to do? But you do a little bit of algebra, and I mean, this is why I love math. I got to be honest. I know engineers, you're like, just punch it into the calculator. But hopefully you can get a little bit of joy. Okay, so there's that. Are there any other questions? I don't want to blow ahead. We got this? Yeah, what do you think, Michael? No, you aren't. You got it figured out. It takes a minute, doesn't it? Yeah. So no, this is it's so simple at the end that you think, how could it happen? You're like, how could that be? But yeah, it's beautiful. Okay, let's move on. Anything else? Yeah, Red. Wait, let me number these so that we got 1, 2, 3, 4. You're talking about number 3? Number 2. Wait, what disappears? The numerator? Yeah, the numerator. These two. Well, I have 4 minus x squared plus x squared. You have a negative apple plus an apple. Sorry, gives you nothing, right? So, I mean, I could put 4 minus 0 here if you prefer, but yeah, it's minus x squared plus x squared is just, yeah, so I just combined those. That's all I did from here to here. It's just minus x squared plus x squared is nothing. So the only thing that's left is the 4. Yeah, anything else? Yeah, Hayden? Okay, yeah. So it's combining the like terms here. Yeah, okay, thank you. Anything else? Other things before we move on? Yeah, no, yeah, good. Okay, let's see. What do we got next? So next we have this thing. We've got a parabola, and so this. Notice that we're rotating around the y-axis. Don't fear; it's going to be okay. Surface area is so much easier than doing all of the shells and washers. You don't have to. It's the same formula every time. Here, I'm just going to copy this because even though I'm pretty sure I have enough room on this slide, it'll be a lot easier if I just change it over. So first things first, you know the first thing you're going to have to do is to write down the formula and do the derivative. So you can do that. Well, once I get this over here, you will. Okay, paste it back in there. Beautiful. Let me write the formula for you because you're still probably a little bit not familiar with it. So the way I remember it is, I think in terms of finding the surface area of a cylinder. Surface area of a cylinder is 2 pi r times h, but instead of h, we're going to put the arc length. So 2 pi r h, but now you're going to put the arc length instead, which is the square root of 1 plus the derivative squared. So there you go, and we're going to go from A to B. Now I know you're thinking, we're rotating around the y-axis, so don't we have to change this to dy? No, we don't. We just leave it like this. You'll see. Hayden. R is always, okay, so here's, yeah, R is sometimes the function, but R is always the distance from the axis of rotation to the function, to whatever it is that we're rotating. So yeah, we'll get to R in a minute. So don't worry about R, because yeah, you're right. It's not going to be the function in this case. So that's, yeah, we could, by the way, we could, if you want, change this to dy, but that's going to be way, way more complicated than we need to do. We're going to just stick with the formula the way it is, and it works either way, whichever axis, doesn't matter where you're rotating as long as you keep R straight. So Hayden is right to worry about R. Let's get the derivative though. first. So f prime, and then we'll worry about what r is. So Ethan, what is the derivative of this function? Yeah, just 2x, because the function itself is nice. It's just x squared. So now let's think about what r is. Ooh, this doesn't get any bigger. Well, we'll work with what we got. So r, maybe I could draw in a representative rectangle. There we go. So r is this distance right here, r. Now notice that I'm integrating with respect to x. So that distance better have an x in it. So what is that distance when you use x? Does anyone know what that distance is? What do you think, Carson? It is just x. Yeah, distance from the y-axis is x. That's what it is. So that distance r, it is just x. So there you go. So f prime is 2x, r is just x in this case. So this one actually is super easy. So let's go ahead and do this. So integral, and notice that since this is dx, my a and my b better be values of x, not y. So you have x equals, or a is 1, b is 2. So we go from 1 to 2 of 2 pi times x times this square root dx. So let's see, 1 plus 2x squared dx. 1 to 2. I'm going to put my 2 pi out here, I guess. 1 plus 4x squared. Okay, so let's just zoom out just a bit so you can see it all. I don't know if you can see it all good enough. I can zoom in a minute. I'll just give a minute to take a deep breath and digest that. Now, I don't know about you, but when I look at this, I get excited because I can do that without my calculator. I know that some of you probably are more into using your calculator, but let's do this without the calculator. And then if we need to, we can do it with the calculator just to show you that you can go both ways with this. So take a minute and see if you can strategize. There's a pretty easy, obvious thing to do to be able to do this without the calculator. So take a minute and see if you can figure it out. All right, let's see. Oh, get my random person. I'm sure you've all got your strategies. Braden, what is your strategy for doing this? Yeah, u subs, what's u equal to? Yes. So probably Braden thought the same thing I think, and that is that if you look at that, that's inside the sort of a set of parentheses, if you will. You've got the square root of this thing, and the derivative of that is kind of out here. I mean, I know it's not exactly x, but 8x, it's close enough. So we can work with this. So derivative, I guess I gave it away. The derivative is 8x dx. And I'm going to go ahead and do this the way that I like to. And that is to actually make this rearrangement 1 over 8 radical 1 plus 4x squared times 8x dx. Now, let me just point something out about this before we go on. On the last test, and on the previous test for that matter, but on the last test in particular, we had a couple of substitution problems, and I noticed that those of you who skipped this step, you were more likely to get it wrong. Some of you got it right. You're fine. You're fine. If you can skip this without, making a mistake, that's great. But I find that writing this down really helps me to focus on, okay, I have my du right there, and the 1/8 makes sense as to where it came from. So I know it's a pain, and I remember what it was like taking calculus and just feeling like I have to write so much. It's such a pain. I was as lazy as you were. Trust me, probably more lazy. But the more you write, the more likely it is that you'll get it right. Correct. Okay, so now that we've got this, let's do the substitution. So I've got 2 pi. Oh, I left off my limits. That's okay. Times the integral of 1/8 radical u times du. So notice that right there, that is du. I'm going to rewrite this one more time just to, let's see, this is pi over 4 times u to the 1/2. Just to make it a little bit easier for whoever gets chosen. Who is it? Darren does. Darren, you know the antiderivative of u to the 1/2, don't you? Oh, yeah, okay, sorry, I got ahead of you there because I was like, yeah, you know it. And especially when you said 2/3, I figured you're there. Oh, I don't need a plus c because this will be a definite integral. Yeah, so be careful with all of these like antiderivatives. I know that you get cocky and you think, oh, you know this, you don't need to think about it, but sometimes it pays to actually write it out carefully. Okay, onward. What's next? Oh, let's go back to x. So what was u? Oh, u is 1 plus 4x squared. Okay, so I've got pi over 6 times 1 plus 4x squared to the 3/2. All of this evaluated from x equals 1 to x equals 2. So 1 to 2. So did it look okay? Because now the rest of this is just plugging in numbers. So I don't think we're gonna have trouble from here on. Okay, so let's do the rest of this. We've got pi over 6 times, let's see, when I plug 2 into that, 1 plus 4 times 4 is 9. I better write it out. That's going to be 9. Isn't that convenient to the 3/2? Oh, and not so convenient with the lower limit. Pi over 6 times 5 to the 3/2. So I guess this is going to be pi over 6 times, let's see, 9 to the 3/2 is 27. Minus 5 radical 5. So that's not as pretty, but good enough. Box that up. Be happy with it. Okay, so how much time we got? We got at least 10 more minutes until, wait, it's 50, right? 45 you have to leave, but 50 is when the bus leaves. Yes, Michael. Oh. Oh, yes, it is. You're right. It's just not as pretty. Okay, I'll fix it. Well, it still is better than a decimal. I don't know. I know some of you are like, no, it isn't. Okay. Well, okay, so that's better. Thank you, Michael. Keep me straight here. Okay, so we need one for the calculator, and then the final one is going to be Gabriel's trumpet, because that one's the best of the bunch. So let's do one for the calculator, and so this one will be a nice, easy one. What I'm going to do is I'm going to rotate, whoops, that was not straight. Let's try again. Well, not as straight, but good enough. So what I'll do is I will rotate sine of x. So this is y equals sine of x. Rotate this around the x-axis between 0 and pi. And I want to know the surface area. Okay, so this one we'll do on our calculators. I think we could do this by hand, but it's going to be really painful. So let's just use the calculator for this one. And so first things first, I'm going to write down the formula to remind you, just in case you forgot, the surface area. So surface area is going to be the integral from A to B of 2 pi. So remember the surface area of a cylinder, 2 pi r times h. But in this case, since this is a curve, we're going to use the arc length. So 1 plus f prime squared dx, or whatever it is. Okay, so let's blow through this. This shouldn't take too much effort. Y prime. Maggie, what do you have for the derivative of sine? Yeah, just cosine. So this is going to be cosine of x. And I guess the r we need to figure out. Ryan, do you know what the r is for this thing? Yeah, so if I drew this as a representative rectangle of sorts, imagine rotating that around the x-axis, you end up with the r. I should have just labeled it r, which ends up being the function. So in this case, we're happy that it is the function. Yes, when you rotate around the x-axis, it is the function, but I wouldn't bank on that for every time you do this. Okay, so my surface area is going to be 2 pi times the function, the integral from 0 to pi, 2 pi times the function sine of x times the square root of 1 plus cosine squared of x dx. Before you get too excited, I guess I should say you can use substitution here, but the substitution is going to get kind of ugly. U would equals cosine, du would be sine dx, and when you got done with all of that, things don't work out as nicely as you might hope, because you end up with the square root of 1 plus u squared, and nothing to deal on the outside for that. Wait. No. You could do u equals 1 plus cosine squared. Oh, yeah, actually, this is really easy. Okay, let's do it with the calculator anyway, just so we can see how this is done. Okay, so here, let me switch over to, here we go. There it is, so that I can show you how this is done. So let's see, go quit. So I'm guessing, so I've got two calculators here. I'm guessing if you have one like the one on my right here, that you're probably good, because when you hit Math 9, where is it, Math 9, you get this beautiful, just fill in the little blanks there for your integral. So you're not going to have a trouble with that. By the way, that's the one, every one of my daughters, when they went to college, there was a sale. I got each one of these for like $80 at Staples, back when Staples was still a thing. It still is? Okay, well, not in Mount Vernon, it isn't. But anyway, so you do Math 9 if you have one of these junkier calculators, and you get that sort of thing, which is certainly not as pretty as the one over on the right. But what we're going to do is we're going to enter the function. So 2 times pi times the sine of x times the square root of 1 plus, in parentheses, we have the cosine of x, close parentheses, squared, and then close parentheses for the square root. And I think that is the function. And then we're going to go from 0 to pi. And it would not surprise me if this turns out to be something really nice. Whoa, go to the error. What error did I have? Oh, I know. Sorry, I need to tell it which variable I'm using, as if it can't figure it out itself. So put the x. So if you have the old school calculator, you do the function, then the variable that you're integrating with respect to, and then the limits. And then let's see if this works. And sure enough, it takes a minute. Oh, beautiful. 14. Is this a multiple of pi? Let me see. Divided by pi? No, it's not. Well, it's probably some square root times pi. But there it is. That's 14.42. That's what you would do if you were doing this for the homework where it says use your calculator. So approximately 14.423. So good enough. I'll round. Okay, one more to do. And oh, sure. You mean the picture? That. Okay, let me zoom in. You want to see the syntax? Let's see. Oh, whoops, sorry. I don't know why it did that. There, isn't that beautiful? Yeah, I know everyone wishes that they had this type of calculator over here, right? So then you wouldn't have to mess with all that nasty syntax. Why? Why would I want to do such a thing? I've already done it. Maybe later. Let me get to Gabriel's trumpet. All right. Any other complaints before I do Gabriel's trumpet? Yeah, let's do Gabriel's trumpet. Okay, yeah, this is super cool. Okay, last one, Gabriel's trumpet. So we already did the volume, right? So Gabriel's trumpet, this is the y equals 1 over x, where x goes from 1 to infinity. And so let's set this thing up. So if you don't mind, I'm just going to do it like this. So you have 2 pi times the function because we're rotating around the x-axis, so I haven't drawn the picture. Well, I did draw the picture up here. You can see the radius is the function. So 2 pi times that times the square root of 1 plus the derivative of 1 over x is negative 1 over x squared. Okay, so here is this. So this will be 2 pi times 1 over x times the square root of 1 plus 1 over x to the 4th. Now, when I look at this, I think, I don't want to deal with that. But here's what I can do. I can say this, and that is that if you plug in any number, I defy you to find a number bigger than 1, because all the numbers here are bigger than 1. Pick any number bigger than 1, plug it into this, and you'll get, and do the square root, you'll get a number bigger than 1. 1 plus 1 over a million is bigger than 1, is it not? 1 plus 1 over a billion is bigger than 1. So no matter what number you plug in here, it'll be bigger than 1, which means that that integral that I've got written there is bigger than this integral. Just turn this into 1, and you're like, okay, that is bigger than this. So that's the only thing that I'm going to ask you to think about that is not just basic plug and chug. So that this is bigger than this. You might say, well, why do you do that? I thought you wanted to know that. Well, yes, I do, but let's do this one first, because that one's easier. So let's do the one on the right. The one on the right is pretty easy because you know the antiderivative of 1 over x. Let's see who does it. Andrew knows it. Andrew, what is the antiderivative of 1 over x? It is natural log. Very good. So this will be 2 pi times the natural log of x evaluated from 1 to b, and we're going to do the limit as b approaches infinity. And here's where I hope you can see what's going to happen, that this diverges, because when you do the limit as b approaches infinity of natural log of b, you get infinity. So the reason why I did this is because this was too hard, this is easy, this is infinite, and this is bigger than an infinite integral, so it's also infinite. So that thing diverges. Now here's the cool thing about Gabriel's trumpet. If you can imagine this, Gabriel's trumpet has a finite volume and an infinite surface area. So imagine if you were to be tasked with the job of painting Gabriel's trumpet. You would never have enough paint to cover the surface of Gabriel's trumpet. However, if you tipped the trumpet up on its edge and poured the paint in, you would easily fill it, because there's the volume right there. Isn't that weird? How could that be? I love this because it sort of illustrates one of the things about infinity, and that is that whenever you introduce infinity into any system, it produces these weird apparent paradoxes. And we do this all the time when we talk about God, don't we? I mean, God has all sorts of infinite attributes. He is eternal. He is all-powerful. Whenever you do that, you're going to end up with some weird stuff going on, and you just have to accept the apparent contradictions when that happens. So here, mathematicians will tell you that it is an apparent contradiction, not really a contradiction, because there are ways around thinking about this particular situation that help figure this out. Okay, so thanks. Enjoy your tour. If you're going with the bus, you got to go now because the bus is leaving in 5 minutes for those who want to see the HW Hub or whatever they're calling it. Otherwise, you can stick around and chat, but we're done. You have homework for tomorrow, so go, enjoy. So stick around if you